In the figure, we have a series resistor circuit. Part A, what is the current in the circuit shown? Then Part B, draw a graph of potential versus position in the circuit, going clockwise, setting V equal to 0 at the battery's negative terminal. Well, we know in a problem like this, we often want to be able to represent the circuit in a more simplified manner, where you draw your power sources, the 9-volt battery, but then we'd like to be able to represent this as sort of one giant equivalent resistor. Req would be the equivalent resistance for that circuit. When you have resistors in series, the equivalent resistance can be computed quite simply. The equivalent resistance is just the sum of all of the resistances that you have. So here it's 15 plus 4 plus 8, which works out to be 27 ohms. Now, as far as computing the current is concerned, the current I that we compute with the equivalent circuit diagram will be the same current flowing through the real diagram. We'll apply Ohm's law. Delta V is equal to IR. We're interested in solving for I, given the equivalent resistance that we have. So the current is the voltage divided by the equivalent resistance. So it's 9 volts divided by 27 ohms, which is 1/3 of an amp, or if you want, 0.33 amps. Now in Part B, we want to eventually draw a graph of potential versus position in the circuit, and we want to know how much the potential changes as one goes through the battery and through or across each of those resistors. It may be worth first computing how much does the potential change across each of those resistors. So for example, the voltage or potential difference across the 15 ohm resistor will be given by the current that it has, which is 1/3 of an amp, times the amount of resistance, 15 ohms, and so this works out to be 5 volts. In other words, there should be a 5-volt drop from one side of the resistor to the other side. So it'll come down by 5 volts. Likewise, we can compute the voltage across the 4 ohm resistor and the 8 ohm resistor. They all have the same current of 1/3 of an ohm. What they differ by is their resistance. This is 4 ohms, and so this comes down by, we'll call it 4/3 of a volt. And this one comes down by 8/3 of a volt. And we can mark that here. Down by 4/3 volt, down by 8/3 of a volt. And now just a quick check, you'll see if you go up by 9 volts and you come down by 5 and then down by 4/3 and down by 8/3, you'll be back at 0. But what we want to do now is draw a graph. So by definition, we're going to set the potential to be 0 at the negative terminal of the battery. So I'm going to mark that right here with a negative, and I'm going to color all this in green. The voltage, we imagine, steadily increases until you get to the positive terminal of the battery, and at that point we've reached 9 volts. And now what happens is, between the positive terminal and the 15 ohm resistor, that's just a pure conducting wire in which ideally there's no change in potential, and so this graph should look constant for at least a little bit. And then once you get to the 15 ohm resistor, the potential should drop by 5 volts. So I expect this thing to come down by about 5 volts. And so at this point, the potential should be about 4 volts. And so in this region here, this would be the 15 ohm resistor. Now notice that there is a little bit of conducting wire between those resistors and here, and so we can draw a short horizontal line indicating that there's no resistor in between them, but then the voltage will drop by another, we said it was 4/3 volts. That occurs at the 4 ohm resistor. There will be small region in which the potential is constant, and then the potential will come all the way back down to 0, and that occurs through the 8 ohm resistor. I didn't draw these exactly perfect, but hopefully you get the idea. The potential is then constant until you get back to where you started, and that would be at the negative terminal of the battery, at which point it starts to go up again. And so the graph would look something like this.